there, my name is Justin Heckman, and I'm a physics teacher here at Abraham Lincoln High School in Council Bluffs, Iowa. And this is my response video to Veritasium's recent block bullet question. I want to thank you, Derek, for this incredible video and all the incredible videos you do. This one in particular was incredible and impressive because of your interviews with Destin Henry. I found that to be quite engaging for me. Let's look at this and see, from the perspective particularly of the explanations of Destin and Henry. They both predicted that the block would go not quite as high when shot in the side as when shot in the center. And they said this because they believed that the rotational kinetic energy of the block would have to be taken from somewhere. It has to come from somewhere. They said that rotational kinetic energy had to have been taken from the translational kinetic energy or linear kinetic energy of the block after being struck, and that therefore that would basically mean that less potential energy could be, gravitational potential energy could be gained. But when they thought of this, they presumed that the bullet hitting here and the bullet hitting here were transferring the same amount of energy to the block, which is not necessarily an appropriate way to think about this, because a bullet, when it impacts, anytime you have a collision, in fact, very rarely, I would say, in my mind, never, when you have a collision, a transfer of mechanical energy, is it ever, well, let's just say due to the second law of thermodynamics, is it ever 100% efficient? But maybe their assumption was that they were somehow similarly efficient. But clearly they weren't, because the spinning block had more energy than the non-spinning block. At any rate, we do know something that is conserved in this situation, predictably every time, and that would be the momentum of the system. We can say that the momentum of the bullet coming at this block really stood for the momentum, the linear translational momentum of the system. All of the momentum of the system was trapped up in this bullet. And we can say that because the block, from our reference frame, was at rest. And what we can say is, we can look at this in two different ways. We could say these are two different systems, and we could look at how the bullet, as it struck this, had a force being applied onto it. And due to Newton's third law, there was an equal and opposite force being applied by the block, and there was this transfer of momentum from the bullet into the block. But since the bullet actually embeds itself in the block, I like to think of it as one whole system. And since there is no outside force, say gravity, which was taking the same momentum out of the bullet as it went upward to strike it. So the momentum was predictably going down somewhat due to gravity as the bullet went upward into the block, whatever. However, for the sake of argument, if we flatten this out, it would make it easier. But let's just say that let's disregard gravity at this time, or at least say that it's acting similarly on both systems. And that as the bullet strikes in here, the momentum of the system, being no-ish, that outside force, remained constant. So the bullet and the block have some center of gravity. Who knows where this center of gravity / mass is? Let's say it starts out here. And as the bullet transfers upward, it gets closer and closer and closer to the block. And that this center of mass has some velocity. That velocity multiplied by the mass of the block plus the mass of the bullet, that's not very convenient, this product of these things ends up telling us what the momentum of our system is. And that momentum has got to remain constant unless there's a net outside force. And we can look at this from the perspective of Newton's second law, which says that the net force acting on an object is equal to the object's mass times acceleration. Now, this outside net force, well, as I said, there's gravity in here. We could say that the gravitational force was constant. We could throw this in here and look at the change in momentum. But for the sake of this, I'm just going to act like it's not there. And we're going to say that this is 0. And that the mass times acceleration of the system has got to then be equal to 0. But you can restate Newton's second law by saying that the net force is also equal to, well, you could say mass times change in velocity over time, because acceleration is really change in velocity over time, or dv dt. And so we can say that this is true, and what that's basically saying is that the net force acting on the system is equal to the change in momentum, because mass times change in velocity, because mass times change in velocity is momentum, and it's just over the time. And this is stated occasionally, dp dt, blah, blah, calculus, I don't know, I teach high school physics. Anyway, so the point being is that the momentum of this system has to remain constant. Therefore, once this thing is embedded in here, and the collision is done, it has to have the same initial velocity as it launches off as it did in both cases. So, what's the deal with the energy? Well, the deal is this. When the bullet strikes the center, as opposed to when the bullet strikes the outside corner, the bullet striking here embeds itself in the block in such a way that the whole block has to be moved up. The whole inertial mass. That is true here, too. However, since it's off-center from the center of mass of the block, it has a tendency to push this side up more easily, because it doesn't have to actually push the center of mass up as much. So the bullet comes to rest in the block over a greater distance than, say, this bullet does. Now, I suggest to you that that means that this is a more violent collision than that. And in this case, the molecules inside the block get excited a little bit more. Well, maybe a lot more. They get more excited. They're moving faster. So what I'm saying, is that this block ends up having a greater change in temperature, or what we would call thermal energy. Okay? So the block that does not rotate, this block's rotating, so it has kinetic translation, or it has rotational kinetic energy. This one doesn't have that rotational kinetic energy, but it is definitely warmer. And if we had like some really fancy devices, hopefully you've got this there, you can demonstrate that this thing's warmer than that, presumably. I don't know if you can do that or not. Hopefully. Okay, great. At any rate, that's my response video. I do have a request, though. So I'm going to throw this out because I would really love to see someone with great production values, not myself, come along and do a video on what a helium balloon does in a car when it's driving around, starting, stopping, going around corners. I think it's really interesting, and kids don't expect the outcome. As a physics teacher, I'd like to have a video that talked about that with great production values. And I'd also like to see some sort of firearm bullet casing, bullet combos, maybe that were heated, and with a high-speed, I don't know if you can do this, but with a high-speed video, actually videotape the explosion. I think it would be fascinating in terms of this momentum concept we've been talking about, to see, compare what happens to the casing as opposed to the bullet. Because my assumption is that since this bullet here is so much more massive than the casing, that the bullet doesn't fly off like you see in the movies. That there's that the two explode outward. Well, there's probably more pieces than two, but let's presume they come out in two. They explode outward with the same momentum, and that the casing's going faster. And without the actual gun, the massive thing, this bullet is much less dangerous. But I don't know. If you could do that video, that'd be great. And anyway, there is my response video and 2 requests. Thank you.